Hi Year 13. In today's video I'm going to show you how to find the area under a curve which is given in parametric form. So we're going to look at how it's similar to the way that we differentiated parametric curves and kind of make some connections between those, and then I'll go through some examples for you today. So let's think about the setup for what we mean by a curve given in parametric form. So I'm going to put that over here. So we're imagining that you've got some curve that's described by x, which is f of t, and then y, which is given by g of t. Okay, so the variables x and y given as functions of t, which using t normally because it stands for time. Okay, so what we need to do then is to integrate underneath this function. If we were to plot the Cartesian version of this function, we can integrate it by using this kind of sneaking in of hidden terms trick, like we saw when we differentiated. So the integral of y dx is the same as the integral of y times dx by dt dt. Okay, and you've got to imagine then that the dt's here and here are going to cancel out, leaving this term in the middle back again. So let's think about what these three things are going to look like when we get an example going. So y, well, this is going to be a function of t. In fact, using my example, it's given as g of t, but the main point is that it's an expression with t's in. Dx by dt, well, if we differentiate our x function with respect to t, we're going to get another function of t. Okay, so far our integrand is only going to contain t's, and then finally integrating dt means exactly that. We're integrating our function with respect to t. Okay, that's the shorthand that I'm going to use there. Okay. Now, another thing, crucially, if we're integrating y dx initially, and we have bounds on our integral that are given in terms of x, let's say x equals some number here, and then x equals some number here, then in order to turn that into an integration in terms of the variable t, we're going to also need to change these x bounds on our integral into t bounds by using the function up here, x is f of t. And normally this is going to be a quite simple one that's easy to rearrange. So this integral is meant to be turned into the integral of t equals some corresponding value here, so t equals some corresponding value there. And then it's going to be y dx by dt, dt, as before. Okay, so that's another thing to perhaps write down and then remember. Okay, so let's have a look at a couple of examples then. So we've got quite a familiar parametric curve given here. Y equals cos of theta and x equals sine of theta. We're finding the area underneath this between theta equals 0 and theta equals pi over 2. Okay, many of you might recognize this as being the parametric equation of the unit circle, although normally we'd be given this as x is cos of theta and y is sine of theta, but it will give you the same thing. Okay, so let's apply what we've got to our formula here. I would firstly figure out if we need to change our bounds on our integral, and we don't, because theta here is taking the place of what we'd normally refer to as t. Okay, that's our kind of variable that links x with y, so we don't need to change those bounds. So we're going to integrate from theta is 0 to theta is pi over 2, and then y is going to be cos of theta. That's given there. Dx by dt, well, the derivative of sine theta with respect to theta is going to be another cos of theta. And then we're going to integrate d theta. Okay, that's given there. So if you weren't sure about where these things came from, I'm going to rewrite this formula to see where everything came from. So we're integrating y, in fact, let's keep the colours the same, shall we? So the blue part is the y. Cos theta is the dx by dt. Sorry, in this case it's going to be dx by d theta, because that's the variable we're using. And then d theta is just the same d theta there. Okay, so those are the parts that I've used there. Right, let's sort out what this integral is going to be then. So we're integrating, I'm going to drop the thetas because we know what variable we're using, 0 to pi over 2 of cos squared theta d theta. And then in order to integrate cos squared of theta, we're going to have to use a trig identity to sort that out, because we can't really integrate powers of theta without employing some kind of identity. So I'm going to use the identity that has cos squared in it that can be given in terms of cos of 2 theta. So I'm now going to be thinking about this identity. That's going to be 2 cos squared of theta minus 1. That can then be rearranged in order to isolate cos squared of theta. So cos of 2 theta plus 1 divided by 2 is cos squared of theta. And that's what I'm going to use to integrate this. So now I can rewrite this as the integral of 0 to pi over 2 of, well, the half can come out as a constant factor, so maybe let's put that at the front. That's a half. And then I can put in cos of 2 theta plus 1, and then integrate that d theta. Let's sort that out then. So that's 1/2 at the front. Cos of 2 theta integrates to sine of 2 theta. But then because of the 2 in the bracket, we're going to need to divide by that and put another half there. And then 1 is going to integrate to theta when you integrate with respect to theta. Okay, that's our antiderivative. Let's put the bounds on. And then we'll sub those in and see what we get for our definite answer. So this is a half. And then a half times sine of 2 times my theta value, which is going to be pi. And then theta on its own is pi over 2. And then we're going to subtract the values we get when theta is 0. That's a half times sine of 0. And then that's plus 0. And then we can work that out. So firstly, sine of 0 is 0, and then adding 0 is still 0 as well. So we don't really need to worry about this part. It's just the first bracket that has any non-zero values. So what's this? This is expanding the bracket 1/4 times sine of pi, which I believe is 0, and then add a half times pi over 2, which is pi over 4. And that's our final answer. Okay, so that's our first example done. Make sure you're aware of everything that I did in terms of writing out the formula given here, in terms of the various bits I need to kind of figure out. Okay, let's have a look at our second example. I'm then going to do one of the examples from the work I'm going to show you, and I'll leave you to have a go at the rest. And there's going to be some extra questions there that the further maths people can have a look at as well. Okay, question 2. Find the area under the curve given by x equals 2t plus 17 and y equals t cubed minus 1 over t, and that's between t equals 1 and t equals 2. Okay, so again, the first thing I'm going to notice is that my given bounds are in terms of t, so I don't need to change those, because ultimately my integral is going to be in terms of t, so that's what I need to have right away. Okay, let's write down the formula and see what we can do with it. So we're now going to integrate from 1 to 2 of y times dx by dt times dt. Okay, so let's sort out what these things are. So this is the integral from 1 to 2. Y is t cubed minus 1 over t. Dx by dt is just going to be 2. And dt is just going to be on the end there. Okay, let's maybe factor out the 2 to the front as a constant factor, because we don't need to have that inside our integrand. So 2 times the integral from 1 to 2 of t cubed minus 1 over t dt. Now I can integrate what's inside here, so 2 at the front, and then my antiderivative will be t to the 4 over 4, and then 1 over t integrates to natural log of t. So we've got minus natural log of, I'm going to write t just with brackets because my values of t are going to be positive, so I don't need to make this positive if need be. Okay, t equals 2 at the top, 2 equals 1. Let's put in the values and see what we get. So this is 2 times, okay, 2 to the 4 is 16 over 4 minus the natural log of 2. That's the first part. And then we're going to subtract 1 to the 4 is 1 divided by 4, and then minus the natural log of 1. Okay, Right, lots of these terms are going to simplify quite nicely. In particular, 16 over 4 will be 4, and also natural log of 1 is going to be 0 as well, so we can get rid of this term because that equals 0. Okay, tidy up then. So this is 2 times, and then we've got 4 minus the natural log of 2, and then minus a quarter. And then simplifying, that gives me 8 minus the natural log of 2 minus 1/2, which is going to be, what's that, 15 over 2 minus natural log of 2. That's our exact answer. Okay, fab. Again, hopefully that one was all right. What I'm going to show you lastly then is I'll show you one where you do need to change the bounds, and that will be your first example question given on the sheet I'm going to give you, and then you know what to do in that case as well. So, last part of the video then. I'm going to do this final one. So a curve is given by x equals 3t minus 1, y equals t squared plus 1. And I want the area of the region enclosed by the curve and the x-axis between the lines x is 2 and x is 8 this time. So because we want to integrate with respect to t in all of these examples, or maybe theta if theta's involved, we're going to need to change these in terms of t. So when x is 2, that means that 2 equals 3 times t minus 1, and then you can easily solve that quite quickly. Add 1 and divide by 3 gives you 2 equals 1. And then if x is 8, you've then got 8 equals 3t minus 1, which easily again solves for t equals 3. Okay, so make sure that you do that then in order to have your integral bounds in terms of that variable t this time. Okay. Now we're going to write down the formula and we're going to see what we can put into it. So we're going to integrate between t is 1 to t is 3 of, let's firstly write y dx by dt. That's going to be the integral 1 to 3 of, okay, y is t squared plus 1. Dx by dt is just 3. And then it's dt. Okay, right, I'm going to go a little bit faster now, get to the end, so factor out 3. Then I'm going to integrate with the 3 at the front. T squared goes to t cubed over 3. 1 goes to t. We're integrating from t is 3 to t is 1. Or I should say the other way around, but that's fine. Okay, put in the bounds. 3 times, okay, 3 cubed over 3 is going to be 9. T is 3 for that part, and then we're going to subtract 1/3 plus 1. That's going to give me 3 times 12 minus 4/3, which is 3 times, what's that going to be? That's going to be 10 and 2/3, so I think 32/3. And then 3 times 32/3 gives me 32. Okay, that's my first answer. So that's in fact the first question that's on your sheet for today, which is going to be given here. Now, if you're in further maths, I'd like you to also do the volumes of revolution part as well. And people not doing further maths won't know how to do these particular questions, so you don't need to do these bits. That's 4b, 5b, and also if I scroll down as well, there's another one as well at the bottom. Here you go. Let me just highlight those again. So again, if you're not further maths, you don't need to do these bits. And if you are, some of the answers are given for you there, which you're supposed to kind of arrive at when you do the question. Okay, so the first one's done for you. If you could do the rest for me, please, and submit it to the Show My Homework page, that would be great. And if you've got any more questions, please drop me an email and I'll get back to you and give you some more help. All right, thanks, Year 13. I'll see you soon.